So now we're going to walk through the first part of case study ex1, which demonstrates how to apply key operators in the Flux class. And this particular case study shows a bunch of Flux operators, the ones that are listed here, and it uses them to create, reduce, multiply, and display big fraction objects synchronously, which is not the typical use case for using fluxes. However, we haven't really talked about the concurrency stuff yet, so this is the best we can do based on what we've covered. So you can find this in the ex1 project in my reactive Flux folder in my live lessons GitHub repository. We're now in the ex1 project in my GitHub repository, and let's go ahead and take a look at the ex1 entry point class. This is the main entry point into the test program. As you can see here, it registers methods under test, there are 5 of them, with the async task barrier. And this is that clever way that we were able to wait for things to finish running, especially when we have asynchronous operations that are doing their thing in the background. So we register 5 of these methods. We're going to take a look at 3 of them in part 1 here. And then we turn the control over to the async task barrier, which will start out by running all the tasks. Now, in the case of these methods, which are synchronous, run tasks is going to basically block as each one of them gets run. In upcoming lessons, when we have asynchronous methods under test, run tasks will run those in the background, and then the block method will block the caller thread until all the tasks have finished running. And this is important because if the main thread falls off the bottom, falls off the end of main, then that will normally shut the program down, and we don't want that to happen. So we want the main thread to block. When everything's finished, we're going to get the number of tests that ran successfully, which in this case will be 5. So let's go ahead and take a look at the 3 tests we want to look at first, which are the ones that do multiplications synchronously. So let's switch over to Flux ex, and you can see that here's the first test fraction multiplication sync method, and this uses a synchronous Flux stream based on the just factory method. So we start out by creating a string builder that's going to be used to keep track of the diagnostic information we want to print out at the end of these operations. And we start out by saying Flux just. We create ourselves a Flux with 4 big fractions with these numerators and denominators, and they're going to be reduced. Then we're going to go ahead and use the doOnNext action operator to log the contents of the computation. And you can see here, it's just going to call this method, which, as we'll look at real quick, will append the results we put here to our string builder. And so we're going to keep track of basically the unreduced fractions and the reduced improper fraction, and then ultimately we'll get the mixed string when we're all done. We then go ahead and multiply each of the big fractions by S big reduced fraction, which is just a constant that's a big fraction with a large numerator and a large denominator, and it's reduced. So we do that multiplication for each one of the things in the stream. And then the last method here is just the terminal operation, subscribe, which initiates all the processing up here with these other operations. And then it calls it goes ahead and runs synchronously because the publisher is synchronous and everything runs in the calling thread. That is not the most interesting way of using subscribe, by the way. We'll talk a lot more about that when we talk about the concurrent features of Project Reactor. So if all goes well, we'll end up appending the multiply big fraction into the string builder. If something were to fail, we append the error message into the string builder, and either on failure or on normal completion, we will display the results of the string builder as a string. And then we return s void m, which is just an empty mono. And that informs the async task barrier that we're done, and it can decrement its count by 1. And if we reach the end, it'll return. Otherwise, it'll keep going till all the other processing is finished. So here is test fraction multiplication 2. It's very, very similar to test fraction multiplication sync 1. The only difference really being that we use a list of big fractions instead of using the just operation. So this is a little bit more generalizable. And what we can do here is we then use the from iterable factor method, which takes various data structures that are not reactive, like a list, and turns them into reactive data structures, like a Flux. And then we go ahead and use the doOnNext operator, and that's going to log the big fractions as we saw before. As before, we use the map operator to multiply each of the big fractions by the big reduced fraction. And just like as before, we use subscribe to initiate all the processing and handle the results. Once again, everything handled is done in the same calling thread because we're using a publisher that is synchronous. No big deal, nothing has changed, and we return s void m. The third and final method we're going to look at, test fraction multiplication sync 3, is a little different. After creating the string builder, we then go ahead and make a new random number generator, which we'll use in just a moment to generate big fractions randomly. We then go ahead and make ourselves a big fraction array, which has the same values as we've done with the list and just earlier. And this time we use the from array factor method to convert the non-reactive big fraction array into a flux. Here's where things get different. So we store that flux into flux f1, and now we create a second flux, flux f2, which uses the flux from factor method, which is lazy. So from array, from iterable, and just are all eager. They all do their creation in the assembly thread. In contrast, and so they're always going to return the same value. In this case, we use a lazy way of doing things, and what that allows us to do is it allows us to be able to make sure that the make big fraction method is going to be called each time we need it. So it's going to be called multiple times. Now, if you recall, make big fraction is a factor method that makes a very, very large big fraction by making it an extremely large big integer and then a much smaller denominator. So we have the numerator, which is very large, a smaller denominator, and then we reduce those results. So we end up with a random big fraction. And we use mono's from callable, which is also lazily bound, in conjunction with from, which is lazily bound, to make sure that every time we need to make a big fraction, it'll be done afresh with a new random number. Now, how do we make those other big fractions? We use the repeat combining operator. And the repeat combining operator takes a count, and it will generate those things that many times plus one more. So in this case, we get the one that's created here, and then we repeat it 3 more times. So we have a total of 4 random big fractions that are created here. Each one will be different because these calls are lazy. Note that the semantics of repeat in Project Reactor are slightly different from the semantics of repeat in RxJava's observable. In one you can see here, it always does one more than the count you give it. In the one with the RxJava observable, it gives it that many. I don't know why they have them different. Now that we've got 2 fluxes, let's go ahead and say F1 merge with F2, and that will go ahead and flatten flux F1 and F2 into a single flux sequence without doing anything to the values or types in there other than just kind of merging them. Now keep in mind, when we merge the fluxes synchronously, as we're doing here, they'll essentially be concatenated. Were we to merge them in some concurrent application, however, then they could be interleaved. So if you need concatenation semantics, use concat with rather than merge with. Next thing we do is we're going to print the contents by logging them just like we did before. Just like we did before, we're going to go ahead and multiply everything by this reduced big fraction. And then finally, just like we did before, we're going to use subscribe, which will take the results of from array and the transformations that we made throughout that stream, and also the things we got dynamically by using from and from callable and make big fraction. And it'll basically push that through the stream and then output the results just like we did before. And just like we see before, we return s void m. So let's go ahead and run this program. You can see what it produces. It's going to produce results that we're all going to look at in more detail in the second part of this lesson, which are the last 2 methods, which we haven't really looked at here. But here you can see the ones we care about. You can see we have test fraction multiplication sync 1. This is the output. Notice we get these results from using just. Here's the same results from using the from iterable and a big fraction list. And then we have the results for test fraction multiplication sync 3, the first 4 of which are just like the ones before because we use the same values but with an array as opposed to a list or with just. And then the last 4 are going to be much different because these are going to be the ones that are generated using the random number generator. So you can see here that we've got results that are going to go on astronomically long because these are sort of almost arbitrary precision big fractions, but that's just an interesting side effect of using the random number generator in the way that we have. So when we're all done there, we're going to multiply those numbers by the reduced big fraction, and this is the results that get printed out. So that's an illustration of using some of the key operators in Project Reactor in a synchronous way. And then we'll take a look in part 2 at some other interesting ways of using these operators to handle errors and deal with null values.